All right, so fitting models to data, what we're going to do is we're going to have two columns or two rows of data. So in this example, we have the year that this census was taken, and for each year, that percentage of persons 25 or older that are college graduates. So like in 1990, 21.3% of people 25 and older were college graduates. So let's start with talking about scatter plots. So when plotting data, we don't really want to connect pieces like we do in algebra. Like if we have a linear function or quadratic, like plot the points and then connect them. We don't want to do that here because these points are discrete. So discrete means they're just kind of happening on their own. So I already set up the axes here. So my y-axis, I'm looking at the values 21 through 30, just from looking at those output values. And then for years, we're looking from 1990 to 2008. So with the scatter plot, what we're going to do is plot points for each individual data value. So in year is 1990, the value is 21.3. So I'm going to plot a point right there at 1990, 21.3. Then 1992, it was 21.4. In 1994, 22.2. In 96, 23.6. Then 24.4. And 25.6. 26.7. 27.7. 28. And 29.4. Okay, so we have these individual dots for each of the coordinates coming from that data set. Now what we're trying to do here is look at trend. What is the trend of this data? And specifically, we are going to focus on linear trends, which is what's happening here. So it's not a perfect line that goes through every single data value. It has some curve to it, or in fact, what this would do if we try to graph with it, we would have these straight lines between each coordinate, so that slope would be changing a little bit each time. But we're talking about trend, so it's kind of like if we step back from this graph, what are we seeing happening overall? So we see this upward trend, so we can see this idea of a positive slope. We can get an idea of what that slope would look like, and this is where the line of best fit comes in. So the line of best fit is this line that we can draw that is as close as possible to all of the points at the same time. So for this data, what I would do, I'll just try my best with it. It's kind of nice to play around with a ruler with these and just see how close you can get to all of the points at once. Maybe something like, let me actually use my tool for drawing a straight line. So let's see. Oh, this is nice too because I can kind of move the line around. So like this would be too high above all of the data values. This is kind of going through the middle. That seems pretty close to all of them. If I go too low, then I'm missing a bunch of the data values or I'm just not very close. So I think something like this looks like a line of best fit, where it's just kind of going between all the data values. Some are below, some are above. We're going through some of them. That would be our line of best fit. So why we want this line is that we want to get this equation y equals mx plus b. So y equals mx plus b. Because if we have the actual function, we can use that to estimate values. If we have this linear equation that's basically giving us predictions, because like there wasn't a census in 1999, but with this line, we can get an idea of, well, it looks like at that point, 25% of people 25 and over were college graduates. So we can get this idea of predictions coming through based on this line that's best fit for all of that data. So there are two ways to talk about making these estimations with our linear equation. There's interpolation. So interpolation would be like that estimate for 1999. And we could trust that value because we're estimating within our domain and range. So like estimating that in 1999, the value was 25%. Not too extreme there. Sure, in reality, maybe it was a little different, but by estimating within our domain and within our range, we can be fairly confident in our answer that's coming out of that. Extrapolation is when we predict outside of our domain and range. It's like if I made predictions for 2020 and what the percent of college graduates were then, yes, this line might just continue on perfectly and match the value that was true in 2020. But by going outside, so like our data ends at 2008, we're entering a dangerous spot because trends can change. And as we know, big things happened in 2020 that could have had an effect on the data and values. Maybe it switched things around. So we just don't know. So with extrapolation, you want to be careful. So be careful of making predictions beyond your data set, because we don't know if we can trust that trend to continue on. And I'm just going to continue with this video here to go through the actual math. So we want this line of best fit. And there are great big formulas out there that will do this for us. We are not going to use those formulas. We are going to use technology to help us out. So there are ways to do this with Microsoft Excel. I'm going to show you how to use Desmos in this video to do it. Because basically we want to have this table of values. We want to get this scatter plot going. And then using that, we want to make a linear equation to fit that data. So I have steps here that we can follow, but where we're going to start is plugging in our data into Desmos. So let's go over to Desmos here, and we're going to our graphing calculator. Now, in terms of options up here, there's this addition symbol that's for add item. This is near the edit list and hide expression list options at the top here. So I'm going to add item, and I have these options for what I can choose. It says expression, note, table, folder, image, and we want to add a table. This is going to give me an X column and a Y column. In the X column, let's go ahead and type in our X data values. So 1990, 1992. Oh yeah, what's awesome is it starts to fill in the blank if it's following a trend. So like it just filled in 1994 for me. I'm gonna hit enter, and there's 96. I'm just hitting enter until I get to 2008. Okay, then I'm gonna go over to the Y column and start plugging in the Y values. So 21.3, 21.4, 21.3, enter, 21.4, enter. I'm just gonna type away here. Okay, did I do it? It's always good to read through and make sure it's all typed in correctly. Okay, so we have all of our data. And in this graph portion, we can see the scatter plot. As you can see, it's not showing up here, and it's because of my settings. My axes are way off. So I would need to see the x-axis, and you can edit it by going to graph settings. I'm going to change the x-axis to kind of match what we were seeing. I'll go, what are we doing? 1990. Maybe I'll do 1988 to 2010. And then for the y-axis, we can just look between 20 and 30. Oop. Okay. So now I can see my scatter plot coming through here. Yeah. And it should closely resemble what I graphed over here. It might look a little different just from the spacing of things, so that looks pretty good. Okay, getting this equation of the line. So we input our x values, we put in our y values. So the x values are these x1 values, and y is y1. So what we want to do is add an expression. So I'm going to go back to that add item, or you can just click below here, this number 2, that you can just type in an expression. And we want to type in this y1 tilde mx1 plus b. So for y1, I'm going to just type in y1. It automatically puts that 1 as a subscript, which is really nice. So all I did on my keyboard was type y1, and then we're going to use the tilde symbol. So tilde, and then mx1. Same thing with x, I'm just typing x1. It's automatically putting it as a subscript, and then plus b. And this is automatically finding this line of best fit for us. So I was kind of playing around with drawing it. This is actually our line. And we get some statistics here, but we are interested in these outputs for parameters. We have m equals 0.476061, b equals negative 926.615. Those are the values we want for getting our slope and intercept for our linear function. So we have this data. If we want to know what is the line of best fit, it is y equals, we're going to grab that value for m, 0.476061x plus b, which is a negative 926.615. Now that we have this, we can make estimations. And again, if it's interpolation, we could feel pretty good about our estimation. If it's extrapolation, we want to be careful. So what is the expected percentage of persons 25 years or older that were college graduates in 2005? So we're just going to take this function and plug in the year 2005. So let's go ahead and plug that into calculator. 0.476061 times 2005 minus 926.615. And we just want to keep in mind that this is an expected value. It's an estimation. So we expect about, and from the calculator, we could say 27.9% graduates in 2005. Really, it's people 25 years or older, but we want to kind of move through. And this was interpolation, which is great. This one where we're estimating for 2021, this is extrapolation. And we want to be careful with trusting this value that we're getting out, but we can still plug it in. So we're plugging in 0.476061 times 2021 minus 926.615. So let's see what we get for this one. I'm just going to my calculator. And it is 35.5. And I don't know, maybe that was the percent of college graduates. Starting to get pretty high. So not sure. We would need to check the actual census from around this time to see if it actually fits that data. But we have this expected percentage, but we just need to be careful when we're quoting that value.